Happy Physics Day. So just a couple of quick things here. It is National Siblings Day, so wish your sibling a happy day. I don't know, whatever that means to you. I don't have any siblings, so I don't have anybody to call, but whatever that means to you, enjoy it. Today is our review day for Unit 8. Tomorrow we are taking a test. So my intention with today is I don't have a big plan. We are going to regroup at 2 o'clock, so I want to do a couple quick demos at the end, but it's mostly time for us to review and to go through things. So if you have questions, this is a great day to ask those questions. I want to remind you of a couple of things here. One is just what the test is over content-wise. So just if you have not looked lately, just to be aware, we're doing circular motion, gravity, and electricity. So this goes back a little ways because we had, tests and things in there as well. So we're doing circular motion. That's centripetal acceleration caused by a force. That force has got to be something. You should never, ever, ever put an F sub C for centripetal motion or centripetal force on a free body diagram. Okay? We've been saying this for a long time. A force has to be an interaction between how many objects? Two. And you have to be able to name both objects, right? Earth and frog and earth, right? String on earth or string on frog, frog on string. Like you have to be able to tell me what the two forces or the two objects are. So we did a bunch of that. Then we talked about inertial versus gravitational mass. We talked about weightlessness. Then we derived Newton's universal law of gravitation and we used it to do some problem solving. We defined electricity. We did some circular motion problem, like one circular motion problem with that. And then we did our kind of Coulomb's law applied problem yesterday that didn't work super well, but that's okay. And now we're here. So it's not that much wild and crazy stuff. And the reason that we do it all together is because gravitation and Coulomb's law both fit really nicely with circular motion. Okay? So that's the content that we're going over. I did want to point out the homework that is due tomorrow. The Coulomb's law problems on that half sheet will come in with your homework. So make sure that if you have not done that, you do that. Okay? That's going to actually be turned in for homework points. And then this is the homework that I promised that I would put up yesterday, and I did. These are conceptual questions primarily. And then this is the alternative to the applied problem that I threw up there so that you could give it a shot as well. Okay? So that's what's due tomorrow for the test. And then, so I wanted to tell you that. I also wanted to tell you kind of what the test will look like. I have a draft of it, but it's not done. But this is what my plan is. 10 multiple choice questions in class. That's about 4 minutes per question, okay, just to kind of get your brain around that. I'm going to ask that you include work or an explanation for partial credit. I don't need long, drawn-out explanations. If it's a, ratio question and you write out the ratio work, that's what I want to see. So basically what I'm going for is that I want to see explanation so I know where you got an answer and to know that if you didn't get the right answer, maybe I can see some good physics in there, okay? But to be clear, that doesn't mean that if you're just super confident, you can just circle answers and not worry about it, because I do want you to actually explain your work to me too. Just for reference, could you wait? I'm going to be done talking in a couple minutes, and then you guys can do whatever it is that you need to talk about, okay? For reference, so you get about 4 minutes per question, because, I'm plus or minus a few minutes at the beginning so we can get started. AP test is about 1.8 minutes per question. Again, you don't have to write everything out, but it's just to kind of get you in that brain mindset. And then I'm going to give you 1 or 2 free response questions for take home. So we're going to do that as a take home again, just because then we don't have to take more class time. Those will be due on Monday. I feel like that should be okay. That gives you a couple of days to work. If you feel like that's not enough time, let me know. But we'll work on that. The last unit that we're going to start tomorrow, Friday, is going to be a quick one, and then we'll be in full-on review mode. Okay?
Wait, we have one more unit.
What is it?
Circuits.
Oh, I'm good with those.
Cool. Done and done then. I can get you the test now if you want. All right. So that is the stuff that I have prepared to tell you. Okay? Other than that, we can spend the next half an hour or 25 minutes discussing things as a group. I can just let you work. You tell me what's going to be the best for you. Yes?
You have to memorize the constants.
Absolutely not. They are on your sheet. On your you know what I'm talking about, on the yellow sheet? Yeah, they are all on there on the back.
I didn't see it.
It would be, Jonathan, you point out a nice thing that I would encourage you to do, and that is, you've been spending a lot of your year staring at this side of the yellow sheet. It would be a good idea to glance at the back of it at some point prior to tomorrow, right? Just to know where you find things. So you don't have to waste tons of time going, oh crap, where is the universal gravitational constant? Oh, there it is, right? Just so you're familiar with them. Yeah.
Can I sit real quick?
Yeah, of course. Yeah.
Go over some
Yes, absolutely we can. Yeah. So Ian has advocated for doing some homework problems. Would you like to do those as a group? Or no? Are there more than a few people that would like that to do problems? Because I can just come over and work with him too.
Wait, do you mean like homework problems?
Homework problems.
Yeah. I guess we can do that.
Should we do them for like a few minutes and then we can break off? If you know how to do the problems and you want to just move on and do other things, as long as you're quiet, I'm cool with that too. Does that sound okay? We'll record it because there are some people that are gone that may also want to hear them. So you tell me what you want, or other people can jump in. Again, if you don't need them, then feel free to work, but please work quietly so that it's not super distracting to me. Which ones did you want to go over, Ian? Give me a chapter first. Okay. 26 and 28 from chapter what? So if you have either not done your homework or you've done it but you may have some questions, stay with us a little bit here. It might be helpful. Chapter 6. These are problems, right? 26 and 28. All right. Oh, yeah. The roller coaster is 26. Does that sound familiar to you? Okay. Roller coaster car is going over the rise at the top of a 15-meter radius circular hill. At the top of the hill, the passengers feel light with an apparent weight, only 50% their true weight. How fast is the coaster moving? All right. So they're going over a hill like this. All right. So we need to talk about what's going on here. What kind of forces are acting?
Force of the earth.
Force of the earth. Uh-huh.
There's a normal force that's half as strong as the force of the earth.
Oh, okay. So I didn't really draw. So this is the force of the track on the earth. And you asserted not only that there's that, I'm going to call that Fn. I'm going to say on force of track on, let me do this well instead of poorly, car, and the force of the earth on the car, which is Fg. And what did you just assert? You said that Fn was what? Okay, so then the question is why? Where in the world? Because where did you get this?
It said that at the top, its weight is like half or something like that.
Mm-hmm.
And so basically the net force then would be the Fg would be half. I don't know.
So it says the apparent weight is 50% of their true weight. So think about that Bart Simpson elevator problem, right? Apparent weight is the normal force, right? That's the normal force that they're being pushed up with. And so when we're talking about apparent weight, we're talking about normal force. The normal force is half what Fg is. Does that make sense? Because it's 50%. Exactly. So that means, oh, go ahead.
Sorry.
No.
So when they're the same, that's your true weight is the same as your true.
Right. That's when F net equals 0, right? Yes. So here's the game, is that if we write down our F net equation, so let's say that I hadn't found out this little piece of knowledge, right? And I just knew that it was moving and it was going over this track. It's going this way, okay? F net, I know because I drew the free body diagram. I know that F net is Fn plus Fg. If the cart is just sitting there at rest, then we know that these two forces have to be equal because it's not accelerating. But because it's accelerating, So we know that that's equal to F equals ma. We know that this acceleration is what kind of acceleration? It's centripetal, which means that it's pointing which way? Towards the center of the circle, right? Center seeking. So that means that this thing has got to be, FG has got to be bigger than Fn. Does that make sense? Because FG is pointing towards the center of that circle. So FG has to be bigger than Fn. So we can kind of take that. We can say, all right, well, that means this one and this one's going down. And the MA is also going down. We know those two pieces. Now we can take what Nick had said and say, okay, this is 1/2 FG plus a negative FG is equal to M. And they want to know how fast we're moving or something. Is that right? How fast is the coaster moving? Yeah. We said that it's centripetal acceleration. We can, instead of writing a sub c, we could just write, what is it? V squared over r. Okay. And now we're pretty much there, but let's just keep going. Does that sound okay? So we got a 1/2 of FG plus negative 1 FG gives me a negative 1/2 of FG, right? So negative, hold on just a second. Okay, sorry. Negative 1/2, I'm going to write that as mg, is equal to negative mv squared over r. Hey, I noticed that there are a couple things that can be canceled out there. What can be canceled? Mass can go away, which is good. A lot of these problems, masses go away, which is good because that means that everybody's going to feel the same effect. It would be weird if you felt a different effect going over that hill if you were more or less massive, right? So that's a good thing. The M's go away. Anything else that goes away on both sides? Negative signs are gone. And now we can just solve for V. So we've got, what's that going to be? That's going to be G times R over 2. Square root of that is V. I think that gives us, and it's a 15 meter radius. And we know G, so we're good. Does that get you where you need to go? Cool. So the key here is knowing that apparent weight is Fn. The other one that you wanted to look at was 28. Is this a similar problem?
You said apparent weight is Fn.
Mm-hmm. Yep. Unlike a roller coaster, the seats on the Ferris wheels swivel. Oh, I hate Ferris wheels so much. I love I don't know. I just have a thing about Ferris wheels. Can't do it. What's that?
They're slow. They're not like that.
I know.
Do they scare you or you just don't like them?
I freak out. Like I can't do them. I love roller coasters. Like any roller coaster I'm on, but it's great. But like, yeah, I just know I can't do it. Anyway.
I love roller coasters, but I hate water.
I'm not a huge water slide person. Like the ones that are like where I can't see where I'm going, it's the ones that go like straight down. Can't do those. So, yeah.
That's it. One drops.
Those are
Like the tube ones, I'm okay with. Anyway, we got to move on. All right. Unlike roller coasters, Ferris wheels do this. Blah blah blah. Okay, so for those of you that like Ferris wheels, you know this feeling. I know it because I don't enjoy them. An 80-foot diameter Ferris wheel. 80 foot? Who does this? What the heck? Oh my gosh, sorry. Okay. Ferris wheel rotates once every 24 seconds. What is the apparent weight of a 70 kilogram passenger at the lowest point and at the highest point? So apparent weight, what are we looking for? The normal force, right? Do you want me to go through it? Yes or no?
Yeah.
Yeah, let's do it. Okay. So this is 26. So there's this frightening ride. So here is somebody else, not me, up at the top. My kids make fun of me. My husband really likes Ferris wheels, which is good. So like when we're at an amusement park, I'm like, I'll just watch you guys away from the bottom because I can't do it. Tell me about the forces acting at the top. What forces are acting at the top?
FG.
FG is pulling which way?
Towards you.
Yeah. And what else is pulling at the top?
Fn.
FN. Yeah. How about at the bottom? Same. Okay. We doing all right? So let's do the top one first. F net equals Fn plus Fg equals M times A sub C. And what are we actually looking for?
Matt?
We're looking for not mass. We're looking for apparent weight. They're not the same. It's like the whole point of this. We're looking for this one. FG is pointing down and A sub C is also pointing down, right? So these are both negative. A sub C because it's moving down. It's going a circle.
80 feet is 24.
24.
But ACC is
0.38 meters. Okay, thanks. Oh, that's the diameter. So I should divide that. Jeez. Do we even need it? I wonder if it goes away. We'll have to find out. Okay, so that's going to be equal to m times v squared over r plus mg. Does that make sense?
Wait, where's the MG
FG.
from? Oh, yeah.
The important thing here is that this one's negative and this one is now positive. We have to pay attention. It's all about the signs on this one. Yeah.
They're going to be the same apparently at both the top and the bottom.
Are they? Well, I don't know. It's part A and part B. So let's keep going. Let's ask. Or not ask. Let's figure it out. So at the bottom here, F net equals Fn plus Fg equals Ma sub C. And which ones are negative in this case? Is Fn negative? I'm looking down here. Is it pointing in the negative direction or positive direction? Fn?
It's
Positive. Fg?
gotta be negative.
Negative. F, or the net force is positive. So in this case, now we only have one that's negative. So that means when we write this one out, we've got Fn equals Ma sub C plus Mg. So now, Isaac, I'm going to ask you, are they going to be the same? No. Where is the person going to appear to weigh more?
At the top. Bottom.
The bottom, because this one we're adding them together, right? This one we're not. Yeah. Keep going? Are we good?
What was the question?
Question is, what is the apparent weight? So we would need to figure out A sub C in both cases, right? So A sub C is V squared over R, which is 2 pi R over T. Is that okay? So you've got 2 times pi times the radius, which is going to be what, 12.2-ish? And you had the period was 24 seconds. So plug in some numbers. And it told us the mass, didn't it? Does that work? Ian, you look perplexed.
Where did you get the negative S at the top?
This one?
Yeah.
Because the centripetal acceleration that it's experiencing is towards the center.
Okay.
So it's going down.
Okay.
Does that make sense? So the net force has to be going down at the top and it has to be going up at the bottom because it's always center seeking.
Okay.
Yeah. So you will feel like you weigh more when you're at the bottom than you do at the top. This part here is just like the problem that we did before, though. Are there other problems that you need or would like help with? Have you all done the problem from that goes with the apply problem? Have you guys worked on that one or no? It was 66 on chapter 20. Would you like me to put it up on the board for you so you can work on it if you haven't done so yet? Okay. Are there other homework questions before I do that I can help you with? All right. I'll put that up there so you can take a look at it. And then we'll regroup in about 10, maybe 15 if I'm really feeling generous minutes. But I don't want to put it off too much because we got good stuff to do. Hold on just a second. Come on, computer.